The last column you missed.
I missed.
You hit the wrong column.
I'm sorry. This one I have to cross out. I got sidetracked.
You have to resurrect the other one.
And this one, I was. Okay. I'm not going to be a very good computer simulator here. That was. Oh, Ramsey, what was the original data?
The X is blank.
Okay. Actually, we got the television camera ready to I mean, we got an exhibit of a wonderfully typeset table that Ramsey did to show these, but you'll see it in the notes, so we don't have to display it on here. Okay, so now okay, so we got 4 ways to cover this guy. 3 here, 3 here, 3 here, 2 here, 4 there. Nothing's forced unless we get a subsumption. Which we do. Oh, yeah. This one is subsumed now by this. Okay, so now, and then that forces us to take this guy.
Also, O is subsumed by O1, looks like.
Now this one is also subsumed, isn't it? Yeah. Okay. So the subsumption rule is actually proving rather powerful in the small example. In a large example, maybe not so much.
Oh, yeah.
O1 is subsumed by O1 too.
There isn't any. Okay.
001 subsumes 010.
001 has nothing in it. We've already chosen this guy.
001.
We've already chosen this guy as a member of our final set. Now, what are you saying?
010.
Yeah.
And 001.
Okay. This guy is a subset of that one. So throw him out. Okay. Is anybody left?
I've got 2 left.
Yeah.
Take them both.
2 left. You need to take them both because this is the only one that covers B1 and this is the only one that covers B2. Okay, so we have used only subsumption, not greed, in this particular case to show that the minimum cover takes 3 things. Now, in a larger case, subsumption actually is still valuable, but you will also have a strategy of branching. If you want to find the absolute minimum based on of a cover problem, then you have a choice of branching on rows or on columns. You can find a column in which you have maybe 3 choices of which row to do. So you can branch 3 ways, or you can find a row. Or you can say how many rows, I have to take one of these rows, and so you just choose some row that eliminates lots of columns, and use that approach to try to get. Now in this case, we're just looking for a heuristic minimum. We're not looking for the absolute minimum, and the greedy method seems to almost always hit the absolute minimum on a random problem or a real world problem, unless the problem was constructed really devilishly. So that's the idea of minimum cover, and I think electrical engineering have been using minimum cover techniques for a long time, and I think still the best discussion of the issues of that was in Ed McCluskey's book that he wrote about 1960. Very nice examples and description of the methods for solving practical minimum cover problems in a pretty effective way. Although it's in the worst case it's NP hard problem. Now let's see, what time is it getting to be here?
12:08.
12:08. Oh boy. Okay. What other things would you like to discuss in our remaining minutes today? I've got something to bring up then. No. Oh, Arif, you have it?
I just wanted to comment that this kind of techniques are easier to apply on a small one than on a really large one, because on a large one you just don't, in the very first place, the process of simply computing what faults you have in what cases It's an extremely expensive one.
Okay, so yeah, so let's take a look at the real. How does this relate to our real problem? Okay, and what in a random approach is suggested, isn't it? I mean, suppose that you have to choose a row from this 65,000 rows. Well, why not just multiply pi by e or something like that? I mean, take some random inputs and just see how many it covers. I tried that. I don't have my data here, but it was pretty interesting that after I had generated, I should have brought that with me. Like after I had tried 100 random inputs just to see how many stuck-at faults I covered, and I think that there were still something like 20 left that I hadn't covered yet after 100. And after I got up to 400, I think I had all but 6 or something like this. And I was suspicious of those other 6. And I ran another case of 500, and I think I had 8 left. And so there were some that seemed to be hard to cover. So then I kept a scorecard. So I made a table of for each fault of how many times after making random inputs, how many times did that fault get detected? And I found that a great number of the faults were detected about half the time. They seem to be fairly easy to do, but there were some of them that like in doing 300 or 500 random cases, only twice or once or something would this particular gate be found. And so I started to get some feeling for the counts in the columns by taking a statistical estimate. You see, just by random sampling, you can get a feeling for. You don't know what the exact number of X's is in a column, but you have an idea that column is which columns are easy to cover, and so they'll probably just be picked up anyway, and those that are sort of prime targets that are necessary. So when you're faced with a larger matrix, instead of exact information, some kind of statistical approach is suggested to me. And that's when I got suspicious of that one gate that was never that I could never pick up at all. Yeah. Okay. Suppose that let me ask this then. Somewhere along the line, I wanted to talk also about AI, the generalization of these things, but I guess I'll try to sneak that in on Tuesday. Let me ask you this: Suppose we want to do the greedy algorithm, but statistically, what would be the statistical analog of the greedy algorithm? In other words, here we have an exact problem, but let's imagine it was a little bit larger. Maybe it was 30 rows and 50 columns, something like that. And the greedy algorithm would say, choose the row that has the most X's in it. After looking for subsumptions and crossing things out, then choose the row that has the most X's in it, and then remove those columns and apply greed again that has the most X's in the remaining thing. But now that would be for a small example. But suppose we have the thing is so large we don't even want to generate the whole matrix. After all, 65,000 times 800 is a fairly large computation. So really for this problem we should in fact imagine algorithms that would conceivably generalize to the next case of the 16 by 16-bit multiplying. So it would an exhaustive approach of actually generating them all would be completely unfeasible for the next case up of the 2 to the 32 inputs. So how would we do it? How would we do an approximate greedy algorithm based on statistics? What would that be? Let me ask someone who hasn't spoken up yet today, so we get more people. Rich, for example, what do you think?
If you don't want to keep the table around, you could just do it by, just try it. You would have to do something relatively greedy.
Yeah, relatively greedy, that's the idea.
Because the thing is, if you can't generate more than a few at a time, you'd have to pick the best one of the ones you have so far. But I don't see what...
I'm trying to abstract it just to a covering problem, not to specifics of our case. So generating a few at a time.
Well, I don't see how that would be different from what you have. Well, because you would cover a certain number more.
Well, in other words, I wouldn't know what the row is that has the most in it, but by doing a sample, I could guess at a row that would be good. See?
So you generate a few hundred and then guess from that.
Yeah, right. So I might generate 100 things and say which one of these 100 covered the most, and I choose that, and then I reduce and say, you know, of the next 100, which one covers the most of the remaining gates of the remaining faults, and so on. And that would be an approximate greedy algorithm. There's a problem of finding those hard ones. And at random, if you, for example, let's imagine the case of the 16 by 16 case. Suppose there are 2 to the 32 inputs, but only 10 of them ever tweak a certain fault. So then you got the chance of finding a needle in a haystack, and you got 10 possibilities out of 2 to the 32nd. You're not going to find it at random. And so the kind of approach that we were talking about last week, where we actually look at the circuit and propagate values forward and backward, looks like the only reasonable way to do that instead of an exhaustive search. Now, while you're almost all here, I wanted to mention that it's not too good to have people dropping in the middle of the class all the time. So please get your act together. Next week, we might have to resort to closing the door so that you have to pound to get in or something like that afterwards. And also, there's only 21 days until our art show. Remember that too. Okay. But otherwise, I'm very pleased with the way the class is doing. Just show up on time, guys. Okay. That's all for today.